adopted.
Yeah, that seems kind of important. He's an alive person?
He's an alive person. Psychological research. So you're the only person that I know that's working in that sector.
Yeah, let me go. I can
You're probably an all-day with them next semester.
yeah, gosh. I know.
But be glad it's there today.
Oh,
Oh, you know that's it.
I know that's an undergrad.
You know that's it. We couldn't keep the quiz. I know, AI.
They had the project.
But that's not good.
That's one.
It's process happening.
Oh, PL has an exam today.
Right now.
PL, yeah, from 10 to 5.
Fine.
Why? Well, usually I've been told that the PL exam, you can sit there for as long as you need to until you get home. Around 5. You can just go ahead through it. But I think the consensus is that and he was like,
Oh, great. My,
last exam was from 10 to 6.
two of my classes yesterday.
All right.
On final project.
So let's begin. So we will, at the end of last class, we were doing project selection, and I will just go over that to the project selection problem again. Just quickly review that just to have a clear understanding of how the reduction works. Then we will get a high-level overview of what we have done in this course so far, and get a glimpse of what we have not done. In the sense that we are focused on solving problems efficiently, and we will get a glimpse of problems that we do not know how to solve efficiently. Okay? So that's how we will wrap up the course. So let's begin by reminding you what the project selection problem was. So the project selection problem is you're given a DAG, G, let's say, over whose vertices are projects. Okay? So you're given a DAG whose vertices are projects, and you would like to, for every V belonging to the DAG, you have a profit PV given to you, and this could be positive or negative. So that is the money that you make out of that project by itself. So the amount of benefit you get from it minus the revenue you get from it minus the cost you incur. Okay? Okay, so but there is a dependency you can do. So if there is an edge, let's say U to V, before you do V, you need to do. You cannot do V without doing U if you have a dependency for that. Okay, so that is the setup. So the goal is find set of projects, of feasible or valid projects that have maximum total the problem. Again, what is a set of valid projects? Well, a set of valid projects is one where for every project that you're doing, if it has a bunch of dependencies that need to be done before it, those are also included in the set. Okay? So you need to define it. A set S of projects is valid if what rule would you say is required for a set of, how will you express the validity of a set of S of projects? Okay, again, set of S of projects is valid if whenever a particular project is included, things,
Its parent is valid.
it's the things that have edges to it also should be in the set. So how would you write it? Well, if for every V that belongs to S, if V belongs to S, what happens? All the U that have an edge to V also should belong to S. Okay? Any U such that UV is in the graph G. Okay? Okay, so the way we are going to solve this is using network flow. And the way we tried to do it is we formulated a flow problem. So let me just remind you of the flow problem. So the flow problem was you write the DAG, the graph that is given to you. Some DAG is given to you and you just put that down as it is, as is. You add a source and a sink. Okay? Now, what you do is, let me just remember which way it goes. You add an edge from a source to every project that has a negative profit. Okay? So let me give an example. Let me put numbers here that indicate the profit that you have. So 1, 3, -8, -2, 4, -1, 9, -5. Okay, let's suppose this was the setup. Then some things have positive profits, some things have negative profits. So you add an edge from S to everything that has a negative profit, and the capacity of that edge would be equal to the absolute value of the profit. So you have an edge from here to here. You have an edge from here to here. You have an edge from okay. Yes. Okay. So the capacity of this would be 8. Capacity of this would be 2. Capacity of this would be 1. Capacity of this would be 5. Okay. Then you add an edge from anything that has positive profit to 3. So that's the setup. And every edge that was there in the original graph, in the DAG, you put a capacity of infinity. Everything that was there in the original. I'm not going to draw all the infinities here, but maybe I should have done that first. So that whatever with the dependency edges, you add a capacity of infinity. Okay? It's not clear at this point why we are doing this, but is it clear what we are doing? Okay? Okay. So, let's try to understand what cuts look like in this graph. Okay? So, let's here, so think about what's happening to a cut. A cut, capital S, capital T, with the source S on one side, T on one side. Yes?
How you decided to draw the edges from X to a node and from a node to B.
Okay. So first we didn't have little s, we didn't have the sync T. We first had the entire graph that is given to us.
Right.
Every edge inside in that graph, we set a capacity of infinity.
Right.
Then from little s, we added an edge to U, to a vertex V, if its profit was negative.
Right.
Okay? And if its profit was negative, PV, let's say, is negative, we put a capacity equal to the absolute value of this. Okay? If it was non-negative, we put a capacity of, sorry. Okay, so every vertex either has an edge from S or has an edge. I guess if it was 0, it doesn't matter what you do, but if the profit was 0, you don't, doesn't matter. Yes?
So S has edges to all of the nodes?
No. S only has edges to vertex V whose profit is negative.
So, alright, okay, yeah.
Okay?
All those nodes negative.
Yes, they're negative. And V only has, sorry, T only has edges from those vertices whose profits are positive or non-negative. Okay? And it's actually a very clever construction, and you'll see exactly how things will come together. So let's look at any set S, any cut S. Okay? What kind of edges cross the cut? If you can have an edge like this, that is a vertex here and a vertex here. Okay? That's a possible edge. What are the other possible edges? S to a vertex there and something here to a vertex T. These are the three kinds of edges. Okay? So our goal is going to be, we are going to look at, we are going to formulate the problem that the projects we want to select correspond to the projects that are there in the S side of the cut. Okay, so we're going to find a certain cut in which the projects are there in the S side of the cut, and that's the one that we're going to select. Okay, so that is the high level idea, but let's try to see what's going on. So let's try to understand the capacity of the capacity of the cut. Okay, it has three kinds of edges. It has this to this, it has this to this, this to this. So first observation is, if S, and you remove remove the little, this is not a project, right? This is a fake source that we added. So if you look at all the vertices inside, all the projects inside, let's suppose is feasible, is valid. Let's say this is a, should we do this one? Sorry, if T, if this is valid, this side is the one where, if this is valid, what can you say about these edges? If this entire set is valid, what does that mean?
There can be no edge.
There can be no edge going from here to here. If people say that, that's a very crucial point. If the set of projects here is valid, what does that mean? That means any project that we have, any dependency it has is already inside. There is nothing here that can have an edge there. So if this set of projects is valid, then there will be no edge going in. Okay? If T minus T is valid, then no infinite capacity edge property. Is that point clear? Okay? That's the first observation. Let's look at the second observation. What is the capacity of this cut? Well, the capacity of this cut, we have to add two kinds of edges, right? What are the two kinds of edges? These are the edges corresponding to the negative profit. These are the edges corresponding to the positive profit. Okay? So the capacity of the cut, how can I write it? Is summation over all projects in T of what? Such that what? So let me add the S, let me add these edges first. So which kind of project should I look at? Negative profit. Okay. Plus all projects not in T which are positive profit. Not in T. Okay? Is that completely clear? All projects in T that have negative profit, and I have to consider not their profit but their absolute value of the profit, and all things not in T that have positive. Okay? So let's try to understand this a little bit. A little better. So this is equal to, so let's try to express this in terms of, let's write it in terms of things in T. Okay, so this is in terms of in T. So V belonging to T, PV less than 0. Okay, I'm going to write this as the total number of things that have positive profit minus the things in T. Okay, so I'm going to write it as like this. So I take a look at every project that has positive profit and subtract the ones that belong to T. So what is this? All positive profit projects not in T. This is all positive profit projects minus all positive profit projects in T. You agree? So So all positive profit projects not in T is the same as all positive profit projects minus all positive profit projects in T. Look at this quantity. This is just the sum of all positive projects. This has nothing to do with S or T. This is a fixed quantity given for the problem, right? It's some number. There is no choice that you're making is going to impact that, because that's just the sum of all the positive profits. Okay, so good. So I'm going to rewrite that. So let's call this quantity as capital P. That's some independent of what we choose. So that's capital P. This is minus the positive profits in T and plus the negative profits in T, but taking the absolute value. So I'm going to write this whole thing as, and you should see this, convince yourself that this is correct. This quantity is exactly the same as this. P minus just the sum of the profits in T. Why is that? Here we are subtracting the positive profits and adding the absolute value of the negative profits, which is exactly the same as just adding up, subtracting all the profits. So here is the remarkable thing. The capacity of this cut is exactly equal to some fixed quantity minus the profit this whole set is giving you. What does that mean? If you want to maximize the profit, what do you want to do for the cut? Minimize the capacity of the cut. So this expression, this translation has told us that, and by the way, this is a feasible set, right? This is a valid set. If the capacity, there were no infinity weightages. Basically, it has told us that if you give me any valid set, its profit would be exactly equal to P minus the capacity of the cut. Okay, so here is the lemma that we have just shown. For any valid set of projects, let's call it X, we have the capacity of the cut given by one side is T union X, okay, X plus T side, and the other side is whatever is remaining, S union not X, S union V minus X, where V is the set of all projects. So if you look at this cut, the capacity of this cut is exactly equal to the sum of all positive profits, which is some fixed quantity P, minus for any valid set of projects, the capacity of the corresponding cut that I had found out is exactly equal to P minus some fixed quantity minus profit of X. So what's the corollary of this? X is valid set that maximizes profit. If and only if the corresponding cut is minimum. Is minimum capacity. So to find the maximum, the largest set of projects, the largest profit set of projects, what we do is we build this network flow problem and we run our max flow min cut algorithm. And again, when we talk about max flow min cut, we talk about it synonymously. We can pick any max flow algorithm essentially and use that to find a minimum cut. So whatever we have studied, Ford Fulkerson, augmenting path, Edmonds-Karp, whatever, we can just say we use an algorithm to find the minimum cut. Once we get a minimum cut, we can just read out the projects from this. So optimal solution of projects corresponds to a minimum cut in the problem, and minimum cut in the problem corresponds to it. But when we say a minimum cut here, we are really not interested in the edges causing the cut. I mean, we could look at it, but what we are interested in is basically the set of things. Yes?
If I've got it right, we find the minimum cut and the set of projects in T are the values.
Are the solution. So you find the minimum cut, and the minimum cut is given by two sides. You look at the projects that are sitting on the T side, that's what you return as the one that has the highest total profit. Yes?
When you create the set to separate the two,
Yes.
and you have the second, the middle process there,
This edge?
that's not valid,
So this, if this edge existed, then this won't be valid.
right?
So basically we are claiming that whenever T is valid, such an edge will not be there. It's impossible that that edge will be there.
So when we're actually constructing this, is that equivalent of saying every edge that has an infinity in your graph, we would just disregard?
No, very good point. We won't disregard that. When we calculate the minimum cut, a minimum cut will never pick something that has an edge crossing it because its capacity will be infinity. Right? If you're trying to solve the minimum cut problem, you will never want to have an infinite edge crossing the cut. So you will make sure your minimum cut algorithm, whatever algorithm it is, which is a max flow algorithm, will make sure it will never set the cut in such a way that there is an edge like that crossing the cut. But you have to pay attention to it. You must make sure that its capacity is infinity, and you will not ignore it. It will be part of your algorithm. But finally, when you construct the cut, an edge will never be. You remember in your max flow algorithm, you keep pushing the augmenting paths, and how do you get the cut? At some point, you're not able to push any more augmenting paths. Then you find everything connected to S on one side, everything connected to T on one side. That will never have an edge of infinite capacity crossing. Because if there was an edge crossing, then this vertex should have been part of this. Yes?
In the given graph, there is no like a C project that has no edges going out from it.
Yeah.
So will the minimum cut always be the cut from S to?
No. So no. When you say every okay, so your question is, what if the given graph doesn't have a sink? The answer is that situation will not happen, because remember, this is a DAG. Every DAG has a sink and every DAG has a source. There are no cycles. If there was no sink, then there would be a cycle. And remember, there are no cycles. Okay. Any other? Yes.
So for the top and the bottom edge, does it have to be a direct connection from S to the node on the other side?
Yes. Those are all direct edges. These are all direct edges. Yeah. So this edge from S. So the reason this edge is there, because this project has a profit that is -5, and this edge has capacity 5. These are all direct edges. In fact, those are the only edges on the cut. The direct edges from S and the direct edges to T. Those are the only edges in the cut.
So there's no way to have a back direction.
There are lots of edges in this direction. In fact, there are possibly lots of edges of infinite capacity in this direction. But they, remember, they are not part of the cut. The cut only looks at edges in this direction. Yeah.
What if all the profits are positive and there won't be any edge from source to?
Good question. What if all the profits are positive? Then there won't be any. So what would be the minimum capacity cut?
Sum of parts.
Because the minimum capacity cut will have no edges. So that capacity will be 0, and all the projects will be included. Similarly, if all the projects are negative, then there will be no edges going this way, then the minimum capacity cut would be to do nothing. Both of those are optimal, right? Any other questions? Good. Okay, so I wanted to present this because this is a more unusual reduction that we tend to see. Okay, and these are clearly, in fact, one other nice problem for which such a reduction works is vertex cover for bipartite graphs. We won't go over it, but we will talk about related problems in a bit. So the one reason I wanted to also present this is a tool that we often use in algorithms in computer science. We take a problem that we want to solve, we reduce it to a different problem. Okay, and we show that a solution to one problem can be used to obtain a solution to the original problem. Yes?
I'm really having trouble following the last line of 2, where you, when you go from there to P equals minus, or I'm sorry, that equals P minus the sum of P.
Yes, okay. So let's look at what's going on here. This is positive profits. Okay, I'm calling it positive. Technically, it's non-negative, but let's assume it's positive. Positive profits, not in T. You agree that's what this is? What is this? Total positive profit. What is this? Positive profits in T. So all we are saying here is positive profits not in T is the same as total positive profits minus positive profits in T. You get it? So this we have replaced by these two.
Right, it's the next step.
Oh, from here to here.
Yeah.
Good. Okay, so good. So we are so far here. So this I've written down as P, and that's what this is. Okay? What is this? This is the negative of all the positive profits in T. What is this? This is the positive of all the negative profits. Okay? So the positive of all the negative profits is the same as the negative, so by taking a negation and then subtracting those negative profits. Okay, so let's just finish that. It's just an algebra calculation, basically. So let's see. What we are going to prove is the following: summation. Okay, it's all PV. So V belongs to T. Negative profit, but you take their absolute value, plus okay, you're proving that this is exactly equal to minus right? Okay, so let me try to, let's just, maybe the easiest way to think about this is, look at anything that has positive profit. What are we doing here? We are keep putting minus of that. What are we doing here? We are putting minus of that. Okay? So that's clear. Look at anything that has negative profit. What are we doing here? We are taking its absolute value. So if there was a minus 8, we are actually adding 8 here. What are we doing here? Well, we are taking minus and then minus 8. Because we have added over all, everything that is there, positive or negative. So we are doing the same thing. On the left hand side we have 8, on the right hand side also we have 8. Just to illustrate that in the context of an example, let's suppose the PB's values were minus 5, minus 2, minus 8, 1, 5, 3. Let's suppose this is what that was. Okay. What is this quantity equal to?
15.
This quantity would be 5 plus 2 plus 8, right? What will this quantity be equal to? 1 plus 5 plus 3. Okay, and we are taking this and subtracting that. Okay, what will this quantity be equal to? Well, 1, 5 and 3 will all be subtracted because there is negation here, right? So 1 plus 5 plus 3. What's happening to these, the negative ones? Well, we take them as they are. Okay? So minus 5, minus 2, minus 8, but then we are multiplying by minus. So we get, so it's exactly the same on both sides. Okay? It's just a different way of, I think the fact that we put a minus here, that's what's confusing. And the crucial thing is, notice that here we have the absolute value and here we don't. Here we just have the original. The absolute value here is not the, maybe the easier way to say it is, notice that the absolute value of PV is nothing but minus PV. Maybe that's an easier way to do it. Then once you see that, you get I made it more complicated than this. Okay. All right. Okay. Good. So, so people talk as far as flow is concerned. So when we are trying to use network flows, we can use cuts, we can use flows. The standard examples, the ones that we have done, and that's the one you have to worry about as far as the exams are concerned, are where we would want to reduce our problem to a flow problem. But for many other situations, reducing it to a cut problem also comes up, and there are some clever reductions that we're trying to see. Okay, so what this notion of reductions is a very powerful notion that we often use in computing. And when we are doing software development, we often do that implicitly because we have a module that we are just using, making calls to that module. That's nothing but a reduction. You have taken a piece of your code and essentially you're reducing it to another piece because you've shown how to solve this piece using that piece. But there is a very systematic way of viewing these things. Okay, and we are there we are doing it, and the way I would say is that we reduced the project selection problem reduces to minimum cut problem. And when we do it, we really don't care as to how you solve the minimum cut problem. We basically say, if you give me a solution for the minimum cut problem, I'm going to give you an instance of the minimum cut problem. If you go ahead and figure out how to solve it and give it back to me, from that I will construct a solution for the project. Okay? So that's the thing to keep in mind. So we have the one thing that we care about is that it be done efficiently. If it's going to take a long time for you to construct a problem, an instance of the other problem, so for example, if you're making a call to another piece of code, but you're going to spend a lot of time trying to package that, then it's not worthwhile. So whatever reductions you're doing, we will be interested in doing that efficiently. And our notion of efficiency is polynomial time. And that's a very standard notion, and you could argue, why do we care about polynomial time? And there is some compelling mathematical reason, but also there are practical reasons. Okay, when we started off the course, we talked about asymptotic notation, and we defined polynomial time as anything that can be done, any algorithm that takes order n to the c for some c, where c is constant, where n is the size of the problem. So order n squared is polynomial time. Order n log n is also polynomial time. Okay, even though you cannot write it as n to the any number, but it's certainly bounded by n squared. It's also bounded by n to the power of 1.5, right? So it's all polynomial time. N cube is polynomial time. If the input has m and n, this is polynomial time. Order n squared n is polynomial time. So all of these are polynomial times. Okay. So the one of the reasons the polynomial time story is compelling is basically what it says is, if the input doubles, input size doubles, then the running time here increases by a factor of 4. Here if the input size doubles, the running time increases by a factor of 8. So whenever the input doubles, the running time only increases by a constant factor. Okay, the input doubles, it increases by 8 or 16 or something, but it's always a constant factor. On the other hand, if you had something like exponential time, if the input doubles, the running time actually squares. It's not increasing by a constant factor. So that's one of the reasons for understanding why polynomial time is right. Also, from a practical standpoint, we see the impact that when you're working with problems of large size, if you're working with anything that is not polynomial, super polynomial, that actually, unless it's a very, very small function, super polynomial function, it is much more difficult to view it as a practical implementation. For the most part, most of the polynomial time algorithms have good practical implementations. But you also start worrying about, oh, is n cubed the best you can do? Can you do n squared? Can you do n? And if you're talking about large data sets, there it matters a lot. Okay? We are not going to get into those details. We are just going to look at the distinction between polynomial time and not polynomial time. Okay? So for example, for network flows, there are lots of questions as to really what is the running time of network flows. And I said we are not going to get into that in this class. There are lots of good algorithms for network flows. The Edmonds-Scott algorithm that we have mentioned takes running time m squared n, which is a fine algorithm for relatively small graphs, but it is not a good algorithm if you're looking at graphs with million vertices and million edges. That's not a practical algorithm. But then again, there are lots of other algorithms that do better than Edmonds-Scott, so we don't have to worry about it. Once we get it down to polynomial time, there are often techniques you can actually do specific for the problem instance to get it. Okay, so right now we are going to worry about polynomial time versus not polynomial. So what is we will define our notion of a class of problems, P, as set of problems that can be solved in polynomial time. Okay? Two things to make this definition more crisp is, what do I mean by polynomial time? What do I mean by solve? Okay? And of course, it's very clear for most problems, but let's just be very precise. What we will do is, when we talk about polynomial time, we'll always make sure that we're talking about time polynomial in the size of input. Always. And what is the size of the input? It's simply the number of bits it takes to write it down. That's most often, there is a way to specify it, but that's one way we can think of it, the number of bits it takes to write input. Okay? All right. What does it mean to solve? So, in all problems, we will have what kind of output we want. But when we talk about classes of problems, we are going to focus our attention on, I'll just make one more comment about the size of the input. So for example, we talk about graphs, and when the graph is given in an adjacency list form, we view the length of the size of its input as m plus n. Okay, because we have m edges to give and n inputs to give. So that's its size. We sometimes have weights on the edges as well, and we usually just think of that as each weight is just one word. Okay, we don't look at how many bits it takes to write down. But you could, if you wanted, talk about how many bits you need to take to write down, how large is the weight, and you can work with that. But we have mostly worked with a model where we don't care about the length of the words, the weights, we just think of it as one number. Okay, so when we talk about polynomial time, we are going to, when we talk about this complexity, we want to understand which problems are complex and which problems are not. It's very convenient, and theoretically speaking, there is no difference, or essentially no difference. If you look at, focus our attention on problems which are called decision problems. Okay, so these are problems that whose input the question will always be of the form yes or no. So it very simplifies the setup, right? So the question would be, I give you an instance and I ask you, is the answer to this question yes or no? That's all you have written. You don't have to give me the maximum flow or anything like that, okay? So examples of decision problems, we have done many of them, but many of the problems that we don't view as decision problems, we can also view as decision problems. So for example, I could ask you, given flow network G and a number K, is max flow of G greater than or equal to K. Okay. Now you might think that that's maybe easier to solve than actually finding the max flow. It turns out no, it's no different than finding the maximum flow. So but when we pose it like this, then it's really a decision problem. Do you agree? I can quickly check whether your answer is correct or not in some cases, but certainly there is either a yes correct answer, either a yes or no. Okay? So that's an example of a decision problem. Yes?
So do you only care about Boolean decision problems?
Yes. Yes. Yes, no. Boolean decision problems. Okay. So P is a, so by the way, is this problem solvable in polynomial time? What would you do? You would find the maximum flow and you check what its value is. If it's greater than or equal to k, you would say yes. If it's less than k, you would say no. Okay? Similarly, you could ask, given unweighted graph G, is there a spanning tree of weight less than or equal to W? Okay, that's also solvable in polynomial time. Yes?
So to verify whether the given answer is correct, the verification phase may take more than polynomial time. For example, if the decision question asks this, let's consider the case of chess, whether the move is the best move possible.
Yeah.
Then the time required to verify whether the given answer is correct or not may or may not be polynomial. So what happens?
That's true. Except that if the, so let's say the way you're solving this, the way, if the solver can do this in polynomial time, then clearly the verifier can also do this in polynomial time, because the verifier can do exactly the same thing that the solver was going to do and check whether they did it correctly. If there was a way to calculate what the best move in chess was in polynomial time, then if you give me a move from a given position, I will start from the position and find out what the best move is and check whether it's the same as what you gave me. Okay? But it is true that in some cases, solving this problem or checking this problem may not be possible in polynomial time. Okay? Certainly, we are going to look at examples of that. Okay? But to talk about checking and verification, there is actually a slightly different view about it. We will look at that in a moment. Okay. So this problem, you agree it can be solved in polynomial time? What do you do? How do you solve it in polynomial time? Find a minimum spanning tree, run Kruskal or whatever, check to see if its weight is less than equal to. Okay. So, and in general, you take any problem that we have done in class until now, they all are examples of problems that can be solved in polynomial time. Okay, almost all, actually not all. We have looked at some problems that are not examples of polynomial time. Even though we thought that we have solved in polynomial time, it turns out we have not. Okay, we will look at it. But so P is the, so this is our set P. Is the, so shortest path sits here, network flow sits here, spanning tree sits here. These are all problems. And activity selection that we did sits here. Hoffman code sits here. These are all can be expressed as decision problems, and they are all in this infinite class of problems, which can be solved in polynomial. Okay. Okay. So let's look at two examples of problems that two problems. So let me start with one problem that I'm sure you've studied that since elementary school. I give you a number n, and I ask you, is n prime? Okay? Can anybody suggest an algorithm for the problem?
Check the square root if it has.
So you first believe there is the algorithm which is actually referred to as Eratosthenes' seed, came up with more than 2,000 years old algorithm. Same algorithm we learn in grade school. So what do? You divide by 2. If it fails, you divide by 3, divide by 5. So you try, and you can actually try all numbers, doesn't matter. But you can do it in a smart way as well if you want. So you, yes.
What does AS and H say?
AS was activity selection, or what is it, interval scheduling, or whatever it was. Interval scheduling. And now I myself forget what Okay, so here is an algorithm. You take n divided by 2, check whether it's divisible by 2. If it's not, divided by 3, check whether it's divisible by 3. If it's not, divided by 4, even though you don't need to divide by 4, but maybe you do. And you can go until, as was pointed out, you don't need to go beyond square root n, because one of the two factors has to be less than square root n. Okay? So let's assume that in most of these models, we'll assume that division just takes constant time, multiplication takes constant time, basic arithmetic takes constant time. So what's the running time of this? Square root n. So the running time is theta of square root n. Okay? Is that polynomial time? Square root n is of course polynomial. The answer is no. This is not a polynomial time algorithm. Why is that?
To find the square root of n, you also need to.
Oh, that's a question. But notice that you're not finding the square root of n. But we'll assume that square root of n you can also do through finite precision. But we are not even finding the square root of n. We are just keep dividing and checking whether a number has reached that value. So the number of iterations is no more than square root of n. In fact, sometimes it can stop earlier. But this is not a polynomial time algorithm in any way. Why is that? Because it should be time polynomial in the size of the input. Okay? What is the size of the input there? What's the input? It's the number n. Okay? How many bits does it take to write the number n? No, how many bits does it take to write the number n?
Depends on how large the number is.
How many? So, can you express it in terms of n? Log n. The number of bits it takes to write n is log n. Log base 2 of n. So that is the input size. So what is the running time in terms of the input size? It's n to the half, which is 2 to the half log n. So which is 2 to the input size divided by 2. So this is an exponential, it's a horrible exponential now. And rightfully so. In fact, all of us should be very happy that that is the case, because actually not necessarily in this context, but because if this was not the case, then factoring, the problem that we know how to factor, the question of taking a number and finding its factors would become very easy. But if you look at it, all of cryptography relies on the fact that this algorithm is not practical. Okay? And it makes sense because the number n that we will use in cryptography are typically something like 256-bit integer. If you have a 256-bit integer, then the input size is 256. So your algorithm is 2 to the power of 128. That time, nothing will ever complete within that time. Yes?
So your algorithm doesn't run in square root n iterations though? Like
No, it does run in square root n iterations.
Right.
But n is so humongous, it doesn't matter whether it runs in square root. Think of a 128-bit. So when they talk about 128-bit cryptography, they, for example, mean that the numbers you're working with are 128 bits long. So if you have 128 bits long numbers, then n is as large as 2 to the 128. Square root of 2 to the 128 is 2 to the 64. 2 to the 64 is very large. Okay? And you can think of it like that, but the other way to think about it is it's not polynomial time because the size of the input is log n, and your time takes exponential. Okay? So this is not a polynomial time algorithm. It turns out that for this problem, primality, there is a completely different, beautiful algorithm that took, like, I would say, you could even say centuries because of the primality has been studied for so long, and it was solved about 15 years ago. And it was shown that primality can be solved in polynomial time, but it uses ideas from, very interesting ideas from number theory and algebra. So it turns out it can be solved in polynomial time. It does, but it's a very different algorithm. But fortunately at this point, factoring, which is not to check whether a number is prime, is to find the factors of a number that is not prime. Okay, the beauty of this situation is the following. If you give me a number, and if it's not prime, I can quickly tell you it's not prime, because I will check primality and I will tell you it's not prime. But I even then do not know what its factors are. Okay? Factoring is not a decision problem, because factoring I really want you to give me the factors. That is a problem we fervently hope is not solvable in polynomial time, because all of cryptography revolves around that. The fact that that's hard. But I would say most people believe it's not very, very hard. I mean, it's certainly, people believe that it probably is not here, but we don't know exactly where it is. And it turns out that if you allow quantum computing, it can be solved in polynomial time. So it's kind of in a funny state of problems. Okay, so yes.
So if I wanted to know if there is a factor, you can do that in polynomial time, right?
If you give me a number, what's the question again?
So if you want to know if a number, so the opposite of prime is a number that's not factored.
That's true. It's called composite.
It's composite, right?
So
if I want to know if a number is composite, that is a decision, like just yes, no, that can be done in polynomial.
Yes, why is that? Because I told you that primality is in polynomial time. I will just feed it to the primality software.
Yeah.
It will tell me, if it tells me yes, I will say no. I mean, composite is just the opposite, right, of primality.
Exactly, yeah.
So if primality is solvable in polynomial time, compositeness is also solvable. Exactly. And that's a straightforward reduction. So you can check whether a number is, whenever a number is not prime, but I can't give you the two factors that make the number not prime.
Okay.
It's a very weird situation. I mean,
Yeah.
you might think that how else will you know that a number is not prime? Apparently, it's very easy to find out that the number is not prime, but I can still not give you the two factors.
Okay.
And at the moment, the best we know is just keep trying, and that's too expensive. Okay? Okay, good. So let's do one other problem similar to this that we actually have solved. We in fact have gone through algorithm solve it, but it turns out it's not polynomial time in a technical sense. So the problem is and that is knapsack. Okay, something for which we wrote a nice dynamic program. Let me recall to you what the problem was. Well, you had n elements. And you had weights and values, right? So you had weights, W1, W2, Wn, and values, V1, n, and you were also given a weight bound W for the knapsack, and you were asked to, so again, let me formulate it as a decision problem. I could also give you a capital V indicating the value that I want to reach, and I ask you, is there a knapsack weight less than or equal to W and value greater than or equal to V? Okay? That's a valid question I could ask. And now the question I want to know is, does knapsack fit in that bubble of P? Can I put knapsack there? Now if you remember, we went through an algorithm for this, and the algorithm, the dynamic program algorithm was what? We look at let's say this element, you ask, shall I put it in there or not? If I put it in there, I will add the value, reduce the weight. If I don't put it in there, I will make no change to the weight, and I'll ask just reduce it, right? So more precisely, you can write this down. So this is just a yes/no question, so we'll just ask a yes/no manner. So we could say arc I and a weight W was equal to either you pick it, or you have a value, right? You also have a value. So you're looking to see whether the op is true if there is a collection of elements of the first I elements. Collection, there is a subset from first I elements with total weight W and value V. Okay. So how would we do that? We would say op I WV is either you pick the ith element. If you pick the ith element, then its weight should decrease by, the weight of the knapsack should decrease by Wi, and value of the knapsack should decrease by Vi. Or you don't pick the element, in which case the weight is fixed and the value is fixed. But you did this. Okay. So again, there are different variations of this problem. So we may not have written down the exact same recurrence because we are posing it as a decision problem and so on. But the point about this is the running time is, so we have to do this for every possible value of little I, which goes from 1 to n, every possible value of W, which goes from 1 to capital W, every possible value of V, which goes from 1 to V. Okay. In the knapsack problem we looked at, we didn't have to pose it as a decision problem, so there we just had n times W. But whatever it be, the running time of the algorithm is something like n times W. Okay, and V as well if you write it like this. This is our running time. In the earlier version of the problem that we looked at before, I think we had a running time of n times W. Okay, but this is not polynomial time. Why is that? N is fine. There are n different elements, so you explain. But W, this is in the size of the problem. You not write this number W, you only take log of W bits. So imagine W being a trillion. So writing that number down only takes you 12 zeros. right? Or 12 times 3, 36 bits. But here it doesn't appear as the number 36, it appears as the number trillion. Okay? So the running time, even though it's polynomial in n, it's not polynomial in other parts of the input. And rightfully so, because we have compelling evidence that this problem cannot be solved in polynomial. Knapsack is an example of a problem that we call NP-complete, that we'll talk about in a moment, because we don't know how to solve it and we believe it cannot be solved in time polynomial in the size of the input. Okay? Okay, so to understand the notion of NP-completeness, there are two things we have to understand. One is this this definition of this class of problems NP, and the other is the notion of reductions, which you already have a good sense of it, polytime reduction. We have defined this class P, which is a set of problems that we know how to solve in polynomial time. Yes?
So based on what you're saying about like W and then this prime question that we did earlier, let's say a really simple algorithm. I want to put all the values from 1 to n, and n is my input. Is that's not polynomial time.
If you want to print out, so let's say you're asking, I would like to print out all the numbers from 1 through n.
Yeah, or like,
and the input I give you is just little n.
yeah.
Then the answer there is that problem cannot be solved in polynomial time, because to print out each of those things you will take time n, which itself is exponential in the size of the input. That's correct, absolutely right. But in that case you could say that the way it's impossible to do it in polynomial time because you've asked me to print all of those things, right?
Right.
But that's one of the reasons why we formulate these problems as decision problems, because all these decision problems require you to output just one bit. Okay? Now, in order to output that one bit, you have to go through all the n numbers.
Yeah.
Then that will take you exponential time,
Right.
and that will justify that the problem is really hard.
Okay.
But maybe there are ways to do it without having to go through every single.
So what if we switch the problem for the sum of every number from 1 to n, just the brute force of this like 0 plus 1?
You just have to add all the numbers from 1 through n.
And then we are.
That's solvable in polynomial time, because you know that 1 plus 2 plus 3 all the way till n
That's
is.
still in the same bit. It's
Yes,
the same, okay.
exactly. It's not that big. Yes.
It's not clear to me why, if we have capital W there,
Yeah.
it is not polynomial, because this is still polynomial in n and w, right?
It is polynomial in n and w, but remember it should be polynomial in the size of the input. Okay? What is the size of this input? How many bits does it take?
This
Okay, let's take a look at it. You have n elements, right? Each element will give its weight and value. The maximum weight it has could be capital W, no more than that. So each of these takes you log of W, log of capital W. So I would say the number of bits this takes is less than or equal to n times log W. Each of these takes you log W, log W, log W. Similarly, this takes you n times log V. So input size n times log W. So there are two parts to the input. You can think of it as n, and then log W, and then log V.
Because we just have one value of W, and here there are n different elements, each one taking log n.
Log W.
Log W.
Correct. So we have the right dependence on n, but the dependence on W is bad. Okay, so NP stands for non-deterministic polynomial time. Okay? To think about it, there are different ways to think about it. Ignore the terminology there, but the way to think about it is the following. Let's suppose I give you a problem an instance I of problem phi, and for this instance I claim that this is actually, so I remember our problem consists of a yes-no instance, right? So some instances have a yes answer, some instances have a no answer. Let's suppose I tell you that whenever it's a yes answer, I will give you a proof of the yes answer. Okay? So phi is in NP. So problem pi is in NP if for all yes instances we can a Pauli size circuit. That can be verified. Okay, let me just do a couple of quick examples and then we will prove one reduction. Okay, so for the knapsack problem, is there, if the answer is yes for a given instance, what kind of certificate could you give me? So again, knapsack instances, I give you a bunch of items, I give you a bunch of their weights and values, and I ask you, is there a set of items whose weights adds up to W? Or at most W, and its value adds up to at least V. And so that's an instance I give you, and then you say, oh, the answer to this instance is yes. Can you give me a proof of that? What proof would you give me? The items that supposedly give you this knapsack, right? That's how much time will it take you to give me that information? Well, you'll give me the item numbers 1, 5, 7, 13, 15. How long will it take me to verify it? I just have to add the numbers. And remember, the adding numbers, if the numbers are 10 bits long, it's not going to take me more than 10 bits amount of time. So knapsack belongs to NP. Of course, every problem that is in P also belongs to NP, because if it can be solved in polynomial time, you can solve it and give the certificate that whatever you want to do, and I can go ahead and check it. So every problem in P also belongs to NP. Okay? Perhaps the simplest problem that at least the most people consider as the most basic problem, let me introduce to you that one. There's a very clean problem called satisfiability. Okay? The satisfiability problem is it's one of the foundation problems in logic. What I give you is the following. I give you you have Boolean variables x1, x2, xn. So you have n Boolean variables. You construct a formula out of these n Boolean variables and you ask, is there a setting of these Boolean variables that makes this formula be true? Okay. So more precisely, we focus our attention on some kind of format. So we have m clauses clause is of the form variable or another variable or its negation or another variable or its negation. So that's an example of a clause. So an example of a formula is an AND of clauses. So that's an example of formula. Okay, it has 4 clauses and it has how many other variables? Maybe 6 variables? Yeah, 6 variables. And the question, the satisfiability is also a yes-no question. And the question is there a setting for x1, x2, x3, dot dot dot, that makes 5 true. Very simple question, right? How would you try to solve it if given? Okay, can you give me one brute force algorithm for it? So is the question clear? I give you this formula and I ask you, is there a way to set these, remember these are all Boolean, so you have to set them to be true or false. Is there a setting that will make this to be true? So what would you try to do?
Set 1 divided by setting each variable true.
Okay, so how many choices do you have for the n variables?
N plus 2.
2 raised to the power of n, because you have 2 choices for each of them, so you try every single possible choice. 2 raised to n. And then for each of those choices, you plug it in and you see whether it's getting true or not. If it's getting true, you announce it true. If it's getting false for every single one of them, you announce it to be false. Believe it or not, that's pretty much the best way we know how to solve this problem. Okay? For many scenarios. And so SAT, this problem is called SAT. In fact, we are looking at a particular version of it, which is only just three literals per clause. That's called 3SAT. So 3SAT is a problem that we do not know how it's in P, and we believe it's not in P. But is it in NP?
Yes.
Okay, and so if you had to verify to me that this instance is satisfiable, how will you verify to me? What proof will you give me to say, oh yeah, this instance is satisfiable? You will just give me a setting that works. You will say, oh, set x1 equals 1, set x1 equals true, x2 equals true, x3 equals true, you will satisfy. And I can check. When I put x1 equals true, I see that this is true. When I put x2 equals true, I see that this is true. When I put x3 equals to true, I see this is true. And x2 and x3 are both true, so this is also true. So I can check that. So it's almost trivially in NP. Okay? So we have P and NP. So based on what we have observed, you have this class of problems P sitting here, and here the class of problems NP, which includes all of P. Okay? And a $1 million question is, are these two the same? Is P, and it's truly a $1 million question because there is the Clay Mathematical Institute that has put this out as a problem more than 10 years ago now, and people have been working on this for the past 40 years and nowhere near being able to resolve this. Okay. We have a lot of evidence, okay, so we have arrived at the following understanding. we have identified a class of problems called NP-complete. These are, think of it as the hardest, the most difficult problems in NP. Okay? So that we have decided that that's, if you really want to understand whether that problem is in P or not, you should just focus on those because those are the most difficult problems. Why is that? That we have our understanding that the picture, either the world will look like this, or look like this. Either P and NP are exactly the same, in which case there is no problem that is an NP but not in P. Every problem is. Or the picture looks like this. That is, all the hardest problems are, all the problems that are NP-complete problems are not in P. If you take any one of these problems and put them in here, then there is collapse. Okay? So if you come up with a polynomial time algorithm for 3-SAT, then the picture will become this. And you would have won $1 million, you can see. So there is general belief, strong belief, that the picture actually looks like this. It doesn't look like this. There is strong belief that the problems that are NP-complete, we cannot solve them efficiently. There is no way to solve them efficiently. But remember, finding an algorithm for a problem is sort of doable. But to prove that there is no good algorithm for the problem is almost sort of saying that no matter what technique you can bring in, proving these lower bounds are very difficult, very, very, very challenging, because you're proving it about an infinite class of techniques, an infinite class of algorithms. Okay. So what happens often in the study of algorithms is if you come up with a problem, a decision problem or an optimization problem, you try to solve it efficiently, using all the techniques we have learned in class. If we fail, then we try to prove that, oh, it's actually NP-complete. So at least we say that we don't know how to solve it, but maybe there's good reason we don't know how to solve it. Okay? So again, from our picture, all the things we have studied in the course, almost all the things we have studied in the course fall in this category. There are a few things like knapsack is actually here, SAT is actually sitting there, and we looked at independent set. That's also a hard problem. That's here. We know how to solve independent set on trees. That's easy. But independent set on general graphs is actually sitting here. Vertex cover, we have solved it on lines and trees. We can go handle it. But on general graphs, it's sitting here. Okay. Okay. So let me just do one example and then we. Okay, so let me just define to you what is the completeness. So phi is complete if two conditions, phi should be empty, and the second condition is every problem phi prime in NP reduces to every problem pi prime. So this is a very, very strong condition that every single problem in NP you can reduce it to this problem. That means you can, if you can solve pi, then you can solve every single problem. Okay. Again, how do you prove that something reduces to the other? Remember, the way we proved it is exactly the same way that we proved that the project selection problem reduces to min-cut. That is, you take an instance of the problem, you construct an instance of the other problem, such that solutions to the two problems match. Solution to this gives a solution to this, solution to this gives a solution to this. Okay? So the pi polytime reduces to pi prime. If there is a function, so you look at this pi, this is pi prime. Remember, pi can be, the instances of pi are, some of them are yes instances and some of them are no instances, right? If you're talking about decision problems, there is either true or false. Similarly for pi prime, you have yes instances, you have no instances. So one problem reduces in polynomial time to another if you can give a function f that maps a yes instance to a yes instance and no instances to no instances. If there exists a polytime computable function f with this property, that you take an instance I, it will map it to an instance f of I, that is yes. If you take an instance no, then it will map it to okay, and we did this, we gave such a reduction. Whenever we are talking, solving one problem using maximum flow, we are giving a reduction from our problem to maximum flow. We are not talking in the context of decision, but it's very, very similar notion. Okay. So, it turns out the very first main result that was shown was the following one, which we won't go over it. The theorem is satisfiability. 3-sat is NP complete. This was shown by Cook and Levin, and this result has won a Turing Award and a lot of recognition for that kind of work. And then once you prove that one problem is NP complete, you are able to prove many other problems are NP complete by showing that the SAT reduces to that problem. So you can show that SAT reduces to independent set. So I'll just mention examples of problems that are here. Satisfiability, independent set. Vertex covered. We did network flows with only one source and one sink. If you add multiple sources, multiple sinks, but demand that once a particular source only goes to a particular sink, so you have some coordination, those problems are also NP complete. What's called multi-commodity flow. Yes?
Are you saying that every NP-complete problem can be reduced to another NP-complete problem? So
That's true.
That can be reduced to independent set and vice versa?
Yeah, all of them. In fact, it's stronger than that. Every problem in this NP can be reduced to an NP complete problem.
Right.
Again, think of reduced, when you say A reduces to B, that means you're saying that B is at least as hard as A. That's the meaning of reducing. When you're reducing A to B, then B is at least as difficult as A. So everything here is at least as difficult as the whole set of problems. Okay, okay. I think we'll stop here. Let me just say a couple of comments about the final, and then if the people have specific questions, can take it. So, the final will be 2-hour final Turing exams week, and it will be comprehensive in the sense that it will cover the entire course, but certainly more weight will be given to the material that we have covered after, let's say, the first half, in the second half of the course. So you can expect some, so in the midterms we typically had 4 problems, you can expect 5 problems in the final. And I think high level, I don't want to commit to this, but you can expect a problem on network flow. You can expect a problem on programming. You can expect maybe 2 problems from the areas of greedy, minimum spanning tree, shortest paths, graph traversals. And you can expect 1 problem from divide and conquer, asymptotic notation, recurrences. You can assume that stable matching won't be asked. Okay. So this is a sort of a rough.
Okay,
I will also post this on Piazza.
Are we allowed to teach?
We haven't decided. In general, we feel that it's not helpful and it complicates logistics a little bit. So I think we'll go with no cheat sheet. Any questions about? I have some people who have not yet collected their quiz 3 or midterm 2. I have that. Quiz 4, problem set 6, problem set 7 are still being graded. You should get at least know the scores certainly before the final, sometime early next week to mid. Yes. Wait, what's the question? Solution to the problem set? Yeah. Should be posted today or tomorrow.
Could you also put recitation?
Oh yes, that will also be posted. And the review we will have a review next week. Yeah. And the review problems will be posted sometime next week. Yes. Is actually, even though the algorithm is most well-known for, the work has been much more different. How to verify programs. And so he will, the exam is here more or less. Half an hour, 45 minutes to people would come to the talk and he would complain about the choice of color. Because he would say that you have a reason to have these colors. Okay, and if you just don't color it for no reason, then he would get and he would, to some extent, right, so even though I violated all of those things in the class, he would be upset. And he often used his pictures. He was always afraid to make him wrong decision. And it's true, to some extent, they value wrong, right? It seems like half the words should have to be just like, two doors in the bottom. But in reality, of course, So people are very upset
I think he said at some point there might be a bonus question. Every single like
very major. Now, of course, if you find out there are intellectual problems, there is a model of the style of those guys. So you like this made over like once you show this, to show that independent citizen people, all they have to do is you just reduce this. It's not easy, but certainly that's true, but we are not trying to solve independence. We are trying to understand how. Not just show that independence is hard. These are reduced to solve independence. If I was able to solve independence set, I would have been able to solve TSAT. But I already know that so this must be
Like, but sometimes like there's special cases where like you might have overflow cases where you some things might also not be.
So you can do it. And actually, when you look at the two those are very good.
Like last time I forgot to change like when the
but you look at it differently in the constructed
So it's more like when we come up with the idea, either we connect it, then we probably
Like, the numbers grow exponentially, so I haven't fixed the overflow error yet. Like, program assignment 2, I think I got the general algorithms right, it's just I haven't fixed
Tier 1的成绩我这里没有。
是那个数字不是？
这里没有。
你那上。
我现在是所有名单。
你看确定的。那个我能不能给你 check 我那个一个 output 的，看你那个正常 output？ 能不能跟我 check 一个 output， 然后看看我的正常 output？ 没有，不，我
They could very well be here, or it could all be collapsing, so they could very well be the same thing. So it's just that we I think most likely people believe this is the
就是我用2、3、4、5，然后如果那 n 是10的话，我还用24个 combination 就是。用2、3、4、5加到10就是。
Yes here should be yes here only. Can it be yes and no and then?
No. The function should apply to everything here.
Yes,
right? Everything has to be mapped somewhere.
Yes.
But yes should only be mapped to yes, no should only be mapped to no.
But because that is even if we can map all the yes to only no.
我还有个雷点呢，所以我还有个雷点。
好像我也还有一个。
You're right. Except that.
我也好像还有一个，我昨天 take 了一个。
I mean, it's not exactly.
If I add this map which means
then the way you can think of it as if you're doing the reduction the other way, then you can think of it instead of reducing it to pi prime, you're reducing it to the negation of the conjugate of pi.
So it would.
That's how you would do it.
Yes. Reduce to pi.
Oh, okay. What's your name? Has Rukmani spoken with you?
I think this is also capture the relationship between all the
Okay. Okay, let me take a look at it. Can you just send me an email?
Excuse me, I never took a lay day on problem 1, so I don't know if like you could actually submit the program assignment to after the due date.
Yes, you can take a lay day.
Okay.
Yep.
In this definition,
So just you should have total of 3 late days. Total for all problem sets programming assignment together.
Okay.
So you can take 1 late day for programming assignment.
in this definition, where are we capturing that NP complete as the harder problem?
No, when we say that every problem in NP there is system.
But
So when you say reduce means you are at least as hard as the other one. So you're basically saying every problem in NP is no harder than pi, or is at most as hard as pi.
at most I understand.
Therefore pi is the hardest.
Finally, thank you. So,
Yes, so I can show it to what name it can talk about it.
So who collected that?
Sunny?
So what I did was basically just add
NSK group.
yeah. To the graph.
Yeah. When you want to oh, you have, they have.
I think the part that you did not.
Yeah. Because the edges are distinct.
No. Part was that E prime. So you are taking.
E prime if it's
you're adding it to
this.
this.
If it's more, then it cannot. The first one cannot gain.
Why is that? No. E prime is not even an T, right?
Correct. So if you can add E prime to E,
and it is the no. What if it is the highest weightage? That's the question.
If it's the highest weightage, then you remove that edge. Remove E dash.
No, but where we've shown that then E dash is bigger than E.
If it's the highest weightage, then you remove because it forms a cycle.
But it doesn't form a cycle with E.
It doesn't form a cycle with E.
Where is it?
So you add E dash to the chemistry with E.
So let's say.
No, Graph is telling like this. That's what.
So you show that to the guy.
Yeah.
But if it doesn't form a cycle, you can remove the highest from the cycle.
But what if
that is not the highest?
No. It's fine. But what if that is E prime? Then you just remove E prime. Then you still have to. We have not been able to argue anything about E prime versus E.
Oh, so then what is the solution?
So instead of adding E prime, you take out E from G, split it into two parts, and then so this is E, you remove it. Now T prime itself is a spanning tree, not minimum, but it's a spanning tree, so it must have an edge crossing. But that edge should have weight bigger than this, because otherwise this would not have been minimum spanning tree. So let's call this edge E1. So E1 has weight bigger than E. But E prime is the biggest in T prime, so this is bigger than this.
Is NP complete and NP hard same?
No, NP hard is this. Essentially, it's the same thing as this.
So everything lying.
No, it could be even outside NP. It could be outside NP.
Outside NP, outside P, but outside.
Even NP also. It's a bigger set. So the picture should be like this. So this is P. This is NP. NP hard is.
But it will contain NPC.
It has to contain.
So all those
NP hard. Mostly people care about NP complete. Even though they call it NP hard, most of those problems are also NP complete. Because when you say hard, the main point about that is those are harder than everything in NP. That's the main point.
I have a doubt regarding the vector.
Okay, just 1 second. Let me.